In the earlier videos, you studied the interference of waves and strings. Now let's look at the interference of sound waves. In class, I'll show you a demonstration of two speakers that are interfering with one another, and we'll show the interference of these two overlap sound waves. Let's look at the interference first in one dimension as shown down below. Now, what we have is two types of interference that are occurring: constructive and destructive interference. So what we have to do is we'll assume we have two speakers here and here in both situations that are playing the same frequency, and they are also in phase with one another. More specifically, let's assume that these waves are sinusoidal. And there's one wave I've just drawn as a sine wave. And then that the other speaker is also playing the same frequency as well, that is sinusoidal. So here's another wave I've drawn in red, and they're said to be in sync or in phase with each other. If I were to overlap them right beside each other, you would see that they would have exactly the same frequency, and as they are coming out of the speakers, they're moving or oscillating, the source is moving or oscillating exactly in sync with the other one. They're in step with one another. That is what basically in phase means. Now, if they're out of step or out of phase or out of sync, it's like I would take this red wave and shift it a little bit so that the crest meets with the trough. And now if you were to overlap them and they were the same amplitude, then this would be basically result in a wave that has zero amplitude. So in phase means they're basically in step with one another, and out of phase means they're out of step with one another. For constructive interference, we would require two identical waves. They have the same frequency, same amplitude, and also moving in the same direction as shown in this picture. And let's say I move one speaker a little bit back just at the right distance so that you can see that these two waves are overlapping with one another and they're in sync or in phase with one another. As a result, we would end up with a much larger wave with an amplitude that is basically twice of their individual amplitudes if they're both the same amplitude. And when this would occur, we would end up with what's known as Maksim constructive interference. And there would be several positions that you could put these two speakers at apart from one another, which would result in Maksim constructive interference. But there would be a certain condition that would be required. You see, speaker 1, let's say we pick this point here. Speaker 1, that source of sound would take a certain distance to get here. And I'll label that distance R1. And speaker 2 would also have a certain path length that it would take to get to that same location. And I'll label that R sub 2. The difference between these two paths, R1 and R2, is known as the path difference, which we'll label as delta R. For Maksim constructive interference, we want the crest to meet with crest and trough meet with trough. So we want this to be exactly out of sync, one entire wave. So hence, the path difference for Maksim constructive interference must be equal to a multiple of the wavelength. So this path difference must be equal to m, which is some integer value, like m equals -1, -2, 0, 1, 2, and so forth. So as long as it's some integer of the wavelength of the sound produced by both of these speakers. And now for destructive interference. Each of these speakers will have a certain path distance that they will take to get to that place where you're listening to the sound. And hence we'll have a certain path difference, delta R. And we're looking for that specific condition where the crests are meeting with the troughs in each situation as it goes along through here. And that's only going to occur when these two waves are out of phase. More specifically, they're 180 degrees out of phase, as we call it. The two speakers must be producing sounds that are perfectly out of step so that they would produce this destructive interference. And that's going to occur when that delta R, that path length difference, is equal to a half of an integer of the wavelength. So this formula becomes important. For Maksim destructive interference, the path difference must be equal to a multiple of the half integer number of wavelength. So again, m is an integer value ranging from -1, -2, 0, 1, 2, and etc., both to negative infinity to positive infinity. Now you do get situations where you get a little bit louder or a little bit softer in sounds, and those are both constructive and destructive interference, but we're looking for the condition of maximum constructive or destructive interference. These formulas are not on the AP formula sheet. You have to just understand it. Well, if you want to get constructive interference, you want the path difference between these two sources to be out of sync or in sync with each other by a whole wavelength. And if you want destructive interference where you hear no sound at all, then you want the two sources pretty separated a distance such that they're off by in half of a wavelength. Okay, I think you're ready to put this in practice and try the next example.